Hope you can hear me and see the presentation as well. So let's give a couple of minutes for everyone to join, and I can start with the presentation. I guess we have a good number of people that have joined the session, so we can start. So today's webinar, the topic will be beyond inverters, capacitor banks in power factor strategies. So basically, we're going to talk about capacitor bank as a strategy to enhance the power factor and to compensate for the reactive losses in PV plants. So I'm going to be the speaker for today. My name is Enio Gjoni. I'm a senior product owner for the grid interconnection team within RatedPower. My background is in electrical engineering, mainly in power systems, and I've had experience on building network models and running like different power system analysis, such as power flow, contingency analysis, state estimation, optimal power flow, and a variety of other power system analysis. So the agenda for today's webinar, I've divided the webinar in several subtopics. So the first one starting with an understanding of what capacitor banks are and what, in the first place, was what capacitors are. Moving on to the definition of power factors, so defining first what the different types of power in AC systems are and what's the meaning of power factor and why it's such an important metrics for electrical power systems. We're going to move then on to the reactive power compensation with different strategies and the benefits of doing this type of compensation, following by some real life examples. So we're going to jump to the RatedPower software in order to understand how to use these strategies and how to use the capacitor bank strategy within our software. By the end of the webinar, I'm going to save some time for a Q&A session. You can use the question box in the GoToWebinar control panel to write any question or doubt that you will have for the content of this webinar. So jumping to the first subtopic, understanding capacitor banks. So in order to understand capacitor banks, first we have to understand what capacitors are. So capacitors are devices that will store electrical energy by accumulating electrical charges into metal plates that are insulated from each other from a dielectric material. So basically when this device, the capacitor, is connected to a source, these metal plates will be charged. One of them will be negatively charged, the other one positively, and so they can save, and they can have this energy within the store this energy within the capacitor. The capacitor is created out of, as I said, two metal plates of conductive material. They can be either aluminium, silver, or whatever conductive material. The most used one is aluminium. These two metal plates are divided by a dielectric plate that usually is like paper, glass, or ceramic material. And lastly, the capacitor will have two terminals that these terminals will serve to connect to the rest of the circuit. So capacitor bank. So capacitor bank is nothing but a set of capacitors connecting with each other, either in series or in parallel, and with identical ratings. I want to emphasize here the identical ratings part because it's quite important. Having capacitors with identical ratings will bring a uniform voltage and current sharing between these capacitors in a capacitor bank, will bring balanced energy storage with them, and overall the capacitor bank will have a more consistent performance when connected to the grid. So capacitor banks are devices that are used in different settings, in industrial ones, for example, compensate for the inductive load of the motors, in commercial facilities, in utility grids, and in generating facilities. And they are used to enhance the operational efficiency and to reduce energy costs. Basically, a capacitor, by releasing the energy that it has stored, it will counteract the power factor lag or the phase shift between the voltage and the current within an AC system, and by doing so, it can optimize the power efficiency. Later on the next slides, we're going to go through how the capacitor bank will counteract the power factor, why it is important, and how by counteracting this power factor lag, it can improve the efficiency and reduce costs. Moving on to power factor. So power factor definition. In order to define power factor, as I said, first we need to define what power is and what are the types of power in an AC system. And I can do that by showing the power triangle. So the power triangle showcases the relationship between different powers, so the real power, the reactive, and apparent power in an AC system. Starting from the real power. So the real power is the component of the power that actually performs useful works in the system, in the circuit. It's this type of power is consumed by resistive loads, and this type of power is responsible for tasks such as, for example, generating heat, or producing mechanical work in motors, or lighting the lights, providing light in the lamps that we use in our everyday life. This type of power, the useful one, is measured in watts. Then we have the reactive component, so the reactive power. So this type of power doesn't do directly any work in the system, but it's useful in order to, and it's necessary in order to operate inductive and capacitive loads of the system. This type of power, it's created because of the phase difference between the voltage and the current that is brought to the system by different inductors and capacitors connected to it. This type of power, the reactive one, is measured in what is known as VAR, so volt-ampere reactive. And lastly, we have the apparent power. So the apparent power is actually the vectorial sum of the real power and the reactive power, and it will represent the total power flow with both of the real and the reactive power components into a grid. This type of power is measured in VA, volt-ampere. Now that we have a definition of what different powers are in the power triangle, we can move on to the power factor definition. So the power factor is a crucial metric. So it's one of the most important metrics that indicates the efficiency of an electrical systems. We can, mathematically, the power factor is calculated by the ratio of real power to apparent power. So basically real power, as we said before, is the useful power, is the power that actually we need, that that we are charged for when we consume it by the system, and it's useful for generating plant, is beneficial to generate. So the power factor is the ratio between this real power and the total power flow. So it represents and it gives us a metric of how efficient the electrical system that we are connected to is. Mathematically, the real power can be calculated as well as the cosine of the angle. It usually is referred to the angle phi between the real power and the apparent power. It's quite important to keep and to maintain the high power factor in order to minimize energy wastage, so to maximize the active power flow in the system, so reduce utility expenses and to assure optimal system performance. The power factor can have a value between 0 and 1, by 0 meaning that it's fully reactive, so we don't have any active component, and by 1 having the ideal power factor, what is also known as unity power factor. So power factor is 1 means it only has the real component, so the useful component. It doesn't have any reactive component in it. It's quite important to measure and keep an eye on the power factor, because the different entities, either consumers or generators connected to the grid, will have certain requirements to fulfill from the utilities where they are connected to, in order to keep the power factor at certain levels. This is explained in this slide. So grid requirements for power factors. So commonly utilities will have this type of requirements. In our case, we will explain that for the PV plants that will be connected to the grid. Commonly in the requirements of the grids, you'll see this sort of diagrams that are they refer to the power factor, the relationship between the power factor and the voltage in the grid. The relationship between the voltage and power factor, and also reactive power, is a close relationship. So if there's high generation of reactive power without sufficient consumption of the reactive power, it can lead to over voltage condition in the system. And in the other hand, vice versa, if the reactive power consumption exceeds the generation of reactive power, you can have voltage drop. And in these cases, we also see the benefit of devices like capacitor banks that can inject reactive power into the system for regulating the voltage level and the power factor. It's quite essential for PV plants to meet these requirements in order to assure like efficient and stable integration with the grid, and also like efficient operation with the electrical grid. But it's also very important for these plants, especially during the feasibility phase, to run different analyses, what are called, for example, as reactive capability analysis, in order to make sure that the plant that they are designing will fulfill the requirements of the grid where they are connecting to. So we need to understand, they need to understand the requirements of the grid, and they need to run the analysis to understand if the PV plant that is being designed can fulfill in all its conditions the requirements of the grid. Since we are talking about grid requirements, I'd like to remind you of an event that RatedPower hosts here in Madrid. It's called Pulse. It will be hosted on the 17th and 18th of April, so next month in Madrid, Spain. It's an event that has a goal of gathering professionals in the renewable sector and to share knowledge with each other, to network and to promote ideas. In this event, myself and the product manager of the grid interconnection team, Suki, we're going to have a presentation with a topic on grid integration studies, on the technical challenges that the utilities have because of the high penetration of inverter-based generators, and the regulatory frameworks that they have come up to in order to address these challenges. You can find tickets for the event in the RatedPower website. Continuing with our presentation, so the third subtopic is about reactive power compensation, different strategies, and the benefit that it brings. In order to understand the compensation, I wanted to show like different examples. So this example is a plant. So it's a network model equivalent of a plant that is without a capacitor bank. Here in this plant, you can observe the equivalent of the PV generator, the equivalent of the power-mounted transformer, of the collector system, of the substation transformer, interconnection line until the point of interconnection. So basically, in an ideal case where the transmission line and the collector system are fully loaded, and the requirement for the point of interconnection, for the power factor in the point of interconnection is at 1, so unity factor, we can calculate the reactive power losses of the plant by summing up the reactive losses for each component. So the reactive consumption of the mount transformer, of the collector system, of the substation transformer, and also the transmission line. So we can come up with what is the value, what is the reactive power losses for this plant. So since we don't have any compensation devices, so we don't have any capacitor banks, there are two alternatives for this system in order to compensate for these losses. So on the right side of the screen, you'll see the PQ curve, which is known as the reactive power capability curve. In this case, it's the PQ curve of the inverter. So in the inner semicircle that you'll see here, so it's the capability of the inverter. So the first strategy that can be used is to reduce the active power output and to limit the active power output of this plant in order for the inverter to gain reactive power capability, so it can absorb or inject. In this case, needs to inject reactive power in order to compensate for the losses of the system. By doing so, it's quite costly because what you are doing is like limiting the active power. So you're limiting then in the end the energy that the useful energy that the PV plant can produce. Another method would be to oversize the inverters, that this is represented by the outer circle in the PQ diagram. By this way, since we have a constant number of modules, so the DC power in the plant will remain the same. So the active power component will remain constant, so we can produce at full capacity. But by increasing the number of inverters, we can gain reactive power capability in order to absorb or inject reactive power in the system if needed. Both of them have their own costs. So the first cost is because we're reducing the power availability, so the energy that you can produce and you can inject to the system. And the second one, it's costly because you need to increase the number of inverters in the system. The third option, the third method would be for using capacitor banks. So here we have the same system, but we can see now that we have a capacitor connected at the MV level of the substation transformer. So basically a very simple formula, and here we're again in an ideal case where the power factor at the point of interconnection is at 1, so the required power factor is at the unity power factor, and we are sizing the capacitor bank as the sum of the total losses of the system. So basically, it will be the responsibility of the capacitor bank to compensate for all the reactive losses of the system, so the capacitor will inject all the reactive power needed. By doing so, on the right side, now you can see a different PQ curve of the inverter where we don't limit the active power output. So the inverter ideally can work at its maximum efficiency, can work at the power factor at a power factor of 1, and ideally can fully generate all its capacity. So the benefits of reactive power compensation, one of the main benefits is the reduction of network losses. So basically a low power factor results in a high current flowing into the system, and then high current means that you have higher resistive losses by the I squared R formula. So basically increasing the power factor will decrease this current, so decrease this type of losses as well. We'll have the benefit of the power factor improvement, as we explained before. So we're aiming to a higher power factor value. It will increase active power availability. This is explained by the PQ diagram before. So we'll have, when we compensate the reactive power losses, we will have the availability of the inverters to generate at full active power output. It will prevent being charged penalties by utilities due to excessive reactive power consumptions. Usually, utilities will charge either consumer or generating plants if they will consume high amounts of reactive power. So these are also added costs for the plants. And by compensating for these reactive power losses, we can prevent these penalties. And lastly, it will improve voltage regulation in the network. As we said, there's a close relationship between the reactive power and the voltage level. So if we have a low voltage level, we can use a capacitor bank to inject reactive power, so to increase and to keep the voltage level at the nominal values. Capacitor banks inside rated power. So we're going to bring some real life example. Before the real life examples, I'm going to just briefly showcase the capabilities of the rated power software. So capacitors in rated power, the rated power will give the ability to the user to use capacitor bank as one of the strategies to compensate the reactive power losses of the plants. The sizing of this capacitor will depend on the systems that are being designed and that they need to be compensated, but also by the target power factor that we're trying to achieve in the point of interconnection. You can see here in the grid point section, in the grid requirements tab, if it's enabled. So if we are enabling the sizing of the plant using power factor requirements, we have the possibility to choose between different strategies with inverters only, using inverters and capacitor banks, or a hybrid version, or using only capacitor banks. So we can set the required power factor. We can as well define the strategies. For example, if we use hybrid version, of using both inverters and capacitor banks, using this slider, we can design which parts of the plant are compensated by which device. And as a result of this calculation, we'll have the power factor at the output of the generating unit inverters, and also like the battery, the storage inverters. As part of the output reports that are automatically generated from the design in rated power, we will have the interconnection facility single line diagram that will showcase the capacitor bank feeder if the capacitor bank is chosen as a strategy to compensate for the reactive power. In this feeder, you will always find the earth disconnectors, circuit breaker, current transformer, a detuned reactor, and a capacitor bank. I want to emphasize here the detuned reactor. We always connect in series a detuned reactor to the capacitor bank. This is because the capacitor banks resonate with the system's inductance. So this resonance will lead into high current flows and voltage distortion in the system, which can bring risk to the equipment and to the stability of the plant itself. And by adding a reactor in series with this capacitor, the overall impedance of this filter is increased, so we can avoid and we can prevent this resonance. Within rated power, we calculate the capacity of this detuned reactor to a fixed 7% of the total capacity of the capacitor bank. As other documents where capacitor bank will be visible are the bill of quantities that will list all the devices that were mentioned before in the SLD, the interconnection facility report, the power flow model, and the CAPEX sheet. As a reminder, you have knowledge base, which will list all the documents in the RatedPower website, and there you can find the interconnection facility methodology and the power factor methodology report, which are like explanation documents that will explain how we calculate the power factor and how we size the capacitor bank within our software. So having said that, we can move to the software itself. You can just give you a minute to sign in. Okay, done. So basically here we are in the RatedPower environment. So I've created prior to the webinar a design where I've used for the same design different strategies to compensate for the reactive power with different required power factor at the point of interconnection. So we can move to one of the examples. So as we said in the grid point section in the grid requirements tab, if enabled, we can choose how we can choose the strategy that we want for the reactive power compensation for this design. In this case, it's a hybrid compensation method using both inverters, so basically oversizing the inverters, and also using capacitor bands. The required power factor at the point of interconnection is at 0.95. Using then the strategy settings, we can define which of the systems are compensating by what device. So basically, by moving the slider, we can say that we want the MV lines to be compensated by the inverters until the station input, and then whatever is in the station, we want to compensate. So in this case, the transformer, we need to compensate it with the capacitor bank. By having different sections, we'll see also the calculation will be going on in the background that will calculate the resulting power factor of the inverter's output, both in the generating unit inverter, but also in the storage on the battery inverter's output. After running the design, we will have different documents that will be automatically generated by RatedPower, where we can see also the capacitor bank within the documents. Another thing to note is the comparison tool, which can be quite useful in these cases. So basically what we can do is like choose two of our designs. In this case, I'm choosing the designs that have like the power factor requirement at the same level at the 0.95 at the point of interconnection, but they use different strategies. The first design will use the inverters only, and the second design will use a combination of capacitor bank plus inverter. So if we go to the comparison tool, we can choose on different KPIs to compare. In this case, I've chosen some that are relevant for the design. We can see here, it's quite interesting that the rated power for the first design is higher and the peak power is higher, but then when it comes to specific production, we have a higher value for the hybrid method. We have a higher energy produced for the hybrid. We have a higher performance ratio, and we have a lower LCOE value as well. So this can be can serve as indicators for a preliminary study in order to choose a reactive power compensation method and to choose the correct one that it fulfills the requirements that we have for our design. Of course, in order to come up with a more detailed analysis on this, we need to do a technical and economic analysis. And for that one, especially for the economical one, we can use our capex tool. So basically, we can set prices for all the materials that we have in the bill of quantities sheets that we can produce. I've already prepared 2 of them. So I've limited the entries here just to the ones that are relevant to the inverters and capacitor banks. So I eliminated the other one. So here we can find the financial analysis, the capex for 2 cases. So this is the case of the design with the inverters only, and this is the case with the hybrid method, both inverters and using both inverters and capacitor bank. We can see here the number of inverters is 87 because we're oversizing the inverter, so we're increasing the number of inverters. And in the other one that we're using a hybrid version, we have 81 inverters, but then we'll have 2 capacitor banks connected to both transformers that are present in the design, where in the first one we don't have any capacitors. We can set prices within our software there. These prices that I've put here are just indicative. I didn't have any idea what the prices were, so it's just like don't take them for granted. And here we can do an analysis of what are the total costs when we put the correct price on that, what are the total costs of methods compared to another method. So we have the economical analysis of each method as well. Moving now to the Q&A section. That was all the content that I had prepared for today. So the first comment is, why do you need 2 feeders for 1 capacitor bank? Actually, there were 2 capacitor banks. So basically what we do, we had 2 transformers. I just had the screenshot ready in the presentation that just showcased 1 transformer, and then in the entrance of the transformer we had the feeder with a capacitor bank. But in reality, the design, the plant had 2 transformers, and each of them had 1 feeder for each capacitor bank. So you will have the number of capacitor banks in our design at the moment will be correspondent equal to the number of transformers in the substation. I hope this answered your question. Okay, now I can see more questions. So what are the downsides of using capacitor banks for reactive power support? So there are some downsides to that. So basically one of them I mentioned before is the resonance issue. So if the capacitors are not properly designed and properly tuned, they will resonate with the inductance of the power system. So this will lead to kind of transient distortion and will lead to potential equipment damage. Another risk would be over voltages. So if not properly designed, the capacitor banks will bring over voltages to the system. If they will inject more reactive power than that they need to compensate at the moment. Other issues are harmonic amplification. For example, the capacitor banks can amplify harmonic that are present in the system, especially if they are not properly filtered. So these are kind of the main concern, the main risk, I would think. Overall, the capacitor bank is a beneficial solution, so it will bring more positive sides and downsides to the system, but of course it needs to be properly, correctly sized and tuned. So should the capacitor bank be scaled in units? Yes, it's true that the capacitor bank should be scaled in units, but not all the times. So basically, a general rule is that if the kVAR rating of the capacitor doesn't exceed the 15% of the capacity of the transformer, then we can use fixed capacitor bank. But then if it exceeds the 15% of the capacity of the transformer, we need to size it in different units in order to operate it more efficiently. This is also like part of our roadmap in RatedPower. So basically, we're going to launch soon a capacitor bank divided in units in order to compensate better and to achieve better results when operating a capacitor bank. So has the software the capability to provide an optimized placement of capacitor banks in powered network given the needed inputs? Basically, now we have just a fixed point. So the capacitor bank will always be placed in the MB side of the power transformer that is present in the substation prior to the point of interconnection. Another question about does RatedPower have the capability to define modular steps required for the capacitor bank? So yes, I said before, this is part of our roadmap. Currently, the software doesn't have the capability to define steps, but it will have soon, and we'll launch it soon, and we'll notify everyone. And I think that also maybe we can do a session about how to use the steps as well when it's launched. So I guess that was the last question. I hope this was informative and gave you some insight about the compensation with capacitor banks and how you can achieve better results in RatedPower. And don't forget that this session will be recorded and will be posted in our YouTube channel, so you can review it anytime there. Thank you very much for attending, everyone.